Hey, welcome back. Scheduled for 1:30, about 10 minutes late. Had some other things coming up. Looks like my stream is running. Seems like excellent health. Um, cool. So let's get started. So this is another installation and like doing engineering in the age of AI work. I have this textbook that I've been using it for applied mechanics 2, so a dynamics kind of course. And I thought I would grab one of the more advanced questions, so chapter 9, which deals with like rigid body motion and what are the equations of motion here. And there's some questions about like, okay, try to integrate this stuff, give it some numbers. And I wanted to see where this leads us when we tell ChatGPT, like, hey, here's the question that I'm trying to solve. Is it going to be a good study guide? Like, will it give us some good information, or is it going to kind of lead us down a weird path? I don't know. This is an experiment. I just figured I would live stream it and kind of keep track of all the things that I'm doing here. So the main thing in this case is like I have this uniform disk rotor, and it tells me to take a look at 916, but I already copied that over here into my problem statement. It's just a schematic of a disk, so a flywheel. So I have this flywheel, but it's connected to a DC motor. So the idea is I can store some energy into this flywheel by giving it some rotational kinetic energy. And then whenever I need that energy back, that electric motor now becomes a generator, and I can take that kinetic energy, turn it back into electrical energy. That's the main goal with these flywheels. So if I have the current in this differential equation with some voltage applied, and L, R, K, and V. Let's see. L is the electrical inductance, R is the resistance, K is electromotive force of the actual motor, and then theta dot is going to be how fast it's moving, and tau equals Ki. So the torque applied is whatever stiff that K times the current. So I want to show that the governing equation is this. So first off, can we even get there with ChatGPT or any generative AI kind of model? And then the next step is see if we can integrate these governing equations and see what happens here. And then look at a couple of different cases. Cool. So a little bit of like motor and flywheel design. I'm going to try, so I copied this text over into a markdown, into a Jupyter notebook, into this markdown cell. I'm going to do a little bit of bookkeeping. So I don't need to tell it that it's as, let's see, as di expressed as, oh, I see, L over di. So this is supposed to say L frac di dt, like that, plus R times I plus K times theta dot. So let's change this into a, oh yeah, dot theta minus V, like that. Let's see how that equation looks. That looks a little better. So I'm doing this because it's a lot easier for a computer to understand some LaTeX equations than it is to understand like copy and pasted PDF sort of work. So I'm doing a little bit of bookkeeping on the front end just so that we have, so this is going to say slash d ot and theta. And I think this was an IG. Let's do side by side like this. So IG double dot theta equals negative B theta dot. And that is Ki. Tau is Ki. And theta dot. So let's change this. And turn this into an equation like that. And let's change these so that it knows what we're talking about. Here, B is that. Okay, now I think we're looking pretty good. Ah, got rid of my image. Why? Let's just copy it over again. Ah, that's all right. It's a flywheel. We know that it's a flywheel. I'll get it back in there later. Okay, so I've got all this, and let's turn it back into one markdown thing all at once. So I can copy this in, and I'm gonna make this big again and go ChatGPT. I need you to help me with a rigid body dynamics problem. And let's just paste in that whole markdown because we made it look pretty nice to us, and let's see if it, to tackle this problem, derive the equations of motion, and look, it gets the equation pretty well. Let's see what this one does. So it solves for di dt. Tau equals Ki. Is this right? Ki into the equation, so then it's Ig theta double dot. And here it messes up like some of this stuff, but it does give us some parameters like that. And then I know we told it to use MATLAB, but I like Python, and oh cool, using some anonymous functions in there. I like Python. So let's change this. We're going to edit. Using Python NumPy and SciPy. Repeat the previous part. So now it's going to rederive this stuff. Well, I say rederive, but really it's taking our input and doing a best guess at the next word coming up, and then it just keeps creating more words that way. So first off, let's check this first part. So we'll take spectacle, copy this, and let's do our own. So paste this into here. All right, so what do we know about this problem? So we're trying to prove that IG theta double dot is negative B theta dot plus Ki. And what did we do here? We said torque is tau times Ki. So I equals tau over K. Rotational dynamics. Why is it tau minus B theta dot? Because if I'm saying flywheel has some torque applied to it, then IG theta double dot equals tau. So where does that B times theta dot come in? Oh, because that's the electrical. Theta dot, rotation rate, torque applied is Ki. Show that the governing equation is, so Ki equals torque and then minus B theta dot. So B theta dot is some kind of damping. All right, so there's a damping between the motor so then IG theta double dot equals tau, which is Ik minus B theta dot, or Ki minus B theta dot. Okay, so it seems like we're doing okay. This one, it didn't really give us a lot of information, right? Like, where did it come up with this equation? For me, I would come up with that equation of saying that sum of the moments around that point G is equal to the change in angular momentum around G, which is ddt of Ig times theta dot. Ig is not changing, so Ig theta double dot. And then the moments that are applied, one moment, the applied torque is that, and then B theta dot is going to be how much damping there is. Okay, so it looks like it got us onto the right track, right? There's a little bit of a magic arrow here about like, okay, seems right, but how would I know whether or not that's right? And now let's see how this one goes. And remember, we said Python in here. And I like Python because I like to use Jupyter. So now I've got a nice interactive kernel here. Okay, so it sets up an equation of state here. So theta, theta dot, and I, because we have a first order differential equation here and a second order differential equation there. Really, we probably don't care about theta, but we'll let it go. We'll let it calculate that theta. Oh, Wow, it tried to actually run the Python code. So let's copy that code, and we want to run it ourselves. Wow, that's pretty cool. Let's always show those details. So it shows you how it set it up, and let's go in there and try to set it up ourselves. All right, so what are we trying to do? We're trying to integrate two governing equations, set the inertia to 0.01, done. Damping ratio is 0.2, done. R is 1, cool. L is 0.75, done. K is 0.03, the electromotive force constant. Even some nicely documented code too. It's almost too nice, right? Like it's not exactly how I would do it, but it's fine. Plot the rotor torque as a function of time for 5 seconds if 1 volt is applied. So we're having a V equals 1 volt constant, and constant voltage, and then ramped voltage. All right. Okay. Yeah, so here we have T and then this V-func. But V-func doesn't actually get used in this. Oh, V equals V-func of T. I see. I don't love that. I mean, I guess it's okay. So the reason that I don't like that is that usually whenever I'm trying to define these equations of motion and like systems of equations like this, I like to have all these arguments have some kind of default argument, but that's okay because we're defining this constant voltage of T and the ramped voltage of T. Yeah, that's okay. So going from 0 to 1 over 5 seconds, min of T over 5 and 1. Oh, interesting. So it takes T over 5 and then also 1. But if I give it multiple values of T, does it? So let's see. T equals NP dot winspace 0 to 5. I just want to see what my input is. Plot T constant voltage of T. Yeah, it doesn't work if I have multiple values of time. I don't love that. And the reason for that is that it's expecting to always return a single value in this case. So it's not actually using a function. So I would say times T to the 0 or something, like make whatever T I give it, I want it to be that same, so that now I can say, all right, from 0 to 5 seconds, this is my constant voltage function. And then let's get this one up there. Because we're going to have the same problem there. T and ramped voltage of T. Let's make sure I ran this function. Let's go 0 to 10 seconds. And I get the same problem. Like, hey, if I'm using min of T over 5 and 1, it doesn't know how to deal with an array. And so instead of that, let's do, I want to say that it's t over 5 and then so if it's t over 5, that would work, but it's going to ramp continuously. So once I get to 5 seconds, I want to turn it off. And then minus t over, I think it's t minus 5 over 5 times t more than equal to 5. I give it a Heaviside function like that. So it ramps from 0 to 5 seconds, and then once it's at 5 seconds, it'll stay at that. And this is either a 0 or a 1 here, and I'm creating a function that has a slope of -1 that starts at 5 seconds to cancel out that positive slope of, or -1/5, really. All right, so there's my inputs, and now I want to go in and solve for so I have initial state, everything's 0. I really don't think we need to solve for theta, but whatever, we can let it go. And our system, let's double check our system. All right, so we had equation 2 is talking about d theta dt, and equation 3 is talking about, or well, this is d theta, so d squared theta dt squared, because it's the change in x2. So that's the angular acceleration, and then this one is describing the current, where the current is used to describe, so k times the current is telling us how much torque we have, and the current is a function of both the applied voltage and then also this resistance, and that k times x2 will be, which one? X2 is theta. Is that right? Oh yeah, k times theta dot. All right, so that looks good, over L, and that's fine. And we're going to solve for ramp. So here's solving for constant voltage, where I like to put these on multiple lines so I can actually look at them. T end constant. What is that? I want to put that down here with our simulation. T end constant. Okay, so for the 5 second versus 10 second, time eval, CONST. Where's time eval? Oh, Lin space time n constant. So do 500. And so we plug in our system time span. So there's the time span, just plugging in these two values. I feel like I might as well just do that, right? Why make it more complicated? The initial state, that one's fine. Initial state, it's all zeros. And then this is the thing that I usually don't like to troubleshoot, is the arguments in my system. So right now there's an argument, and it's a required argument, because if it's not there, then this function will not run. Yeah, so if I say system of time 0 and state 0, 0, 0, if I just want to figure out the initial state, I have to give it something. And I think even if I try to plug in yeah, I have to give it some kind of function of time. So that's why I was changing this to that constant voltage like that, so that it actually gives me a function that can be evaluated at any time and for all time. So I have to give that argument. I would rather have a default and then plug in a different value, use a lambda. Okay, so that one's fine. And again, like I don't, oh yeah, let's say, let's just plug it in. Again, why make things complicated? We don't need all these extra variables. Time eval is fine. 0 to n. So here we're doing like 1. Let's do like 0.1. So we do every 100th of a second. Just adding one value for that 0 point. And then torque is always K times that current. So once we do this solve IVP, now we'll have the solution in Y. So Y2 is going to be our current. Y so our state is theta, d theta dt, and then current is that last value. So Y2, the third output from our solution is going to be the SOLCONST. We'll run that. Sure enough, we get, I don't love that these are on 2 different time scales either. Why would this go 0 to 10 and this one goes 0 to 5? Yeah, if you're gonna do that, then just make it the same time, man. Let's just do T end ramp like this. RAMP. It's driving me crazy. You can't have 2 figures with different x-axes right on top of each other. One is half the time of the other. All right, so now we've got torque going from 0 to 5. Basically, we get to a constant torque value, like the current becomes constant at some point, versus ramping it up, kind of slowly changes, and then by 8 seconds, we're at that constant thing. And I guess that's what this part C is asking. So ramp from 0 to 1 over 5 seconds and integrate for at least 10 seconds. Cool. So, I mean, it looks like we were able to get all the things that we wanted. I went through and troubleshot some of this stuff to see what was going on. Really, I would like to see, since it's just me, like I'm the only one here, I always like to double check that my solutions are actually kind of working. So let's see. Before I start post-processing, so let's do like a plot SOL constant dot T, SOL dot constant. Oh yeah. SOL constant dot Y. Let's look at, so here, if I look at theta, starts off at 0 and then just keeps increasing. That's what I would expect for a flywheel, that the angle would just increase and increase and increase. So then let's look at how fast it's moving. And what we saw in that first one was like roughly constant slope by time we got to about 2 or 3 seconds. And here we're hitting like constant speed. I mean, it's wiggling a little bit. Can't imagine that's let's zoom in. plt.ylim 0.14, 0. Yeah, it's really bouncing up and down. I don't know why it's doing that. I wonder if we change the method. Still about the same. Let's figure out SciPy solve IVP. Really all I need is this. So Redao is an implicit Runge-Kutta. Maybe this LSODA. But we're still getting that, it's kind of jumping up and down. I wonder if that has something to do with our that second variable. Now current is pretty steady, right? And now let's look at it. Let's zoom in to 0.8 and 1. 0.98 and 1. Still looks pretty steady, right? So that's interesting that we're getting that it's moving at a constant speed, but not like a really constant speed. And that's why I like to check each of my variables and make sure that it's actually doing what I thought it would do. For the most part, I mean, it seems like it's doing what a motor what I would expect a motor to do. When I turn the voltage on, it starts moving, like it starts moving really fast, and then at some point it hits its constant speed. Like every motor for a given voltage is going to move at some value if there's no like counter torque on it. So it seems like it's doing what it's supposed to be doing. Oh, you know what I haven't checked on in a while? Yeah, no chat, but that's okay. Keep above. In the torque, ramped voltage. Cool. So it seems like we can get some pretty good work out of ChatGPT even for like these advanced kind of like systems and mechanics kind of problems. Pretty exciting. It's a crazy world that we live in, right? I just took a textbook problem, and within about 30 seconds we had an answer, and then maybe 20 minutes later we've kind of worked through and made sense of what's going on. All right, cool. Hope you join another time or watch some other time, and I'll keep posting these experiments. Maybe we'll try some other textbook stuff maybe next time. But all right,